Okay, good morning everybody. Hello, welcome. We've got quite the extravaganza of an activity for you today. Fantastic topic, absolutely wonderful. We're going to take a break from the actual rational functions, but they do kind of technically sneak themselves in here, kind of behind the scenes a little bit. We'll get to that in a moment. But big picture here, this section is super critical for understanding all of scientific data, okay? I saw a lot of you are gearing up for physics next year. This is going to be very important, but even if you end up in some other scientific related field or even engineering or any application, anything that involves actually graphing data, you will use this terminology all the time, okay? So definitely the rest of your math life, the rest of your science career, whether that begins or ends in college, is up to you, but you will need this stuff today. So listen up. What I have for you is direct, joint, and inverse variation, okay? You read about it over the weekend. This was part of your 3 sections of notes last weekend. And that's it, just these 3 things. And so I'd like to highlight and come at it from a different perspective than the textbook will, and that is one of physics. So what are each of these things? These are all types of relationships. Direct, joint, and inverse describe how does Y vary with X. And yes, that is the correct vary. It's not a lot of really, really, very, very blue. No. How does it change with X? Suppose that should be a question mark. Right? When X, okay, those are our typical variables from math class, but as we apply this into the world, we might ask, how does, I don't know, rainfall change with temperature? Pick a generic, earth science-y kind of application, right? Or is it the other way around? Is it actually, maybe you want to know, how does temperature vary with the rainfall? Or are they correlated at all, right? And so we have our 3, really 2 types of relationships. There's the direct variation, okay? And that is increases cause more increasing, right? If one goes up, the other goes up. They're in a direct relationship. They are matched with each other. That will always look like this, some positive slope line, usually going through the origin for a direct relationship, not just a linear relationship, but a direct, okay? The opposite of that would be an inverse, and that would be when increases cause decreases, okay? Instead, we have a negative graph, right? As X increases, one goes down. So let's think about some examples here. Let's take humans. For the most part, height varies directly with age. As people get older, they get taller, right? For the most part. What about an indirect relationship? What's something that as one thing rises, something else must go down? The more and more. Let's see. As homework increases, fun goes down, right? More and more work to do, less fun to have, right? You could say there's an inverse relationship. The amount of, well, maybe you actually find the homework enjoyable. How about this? Free time. We'll be a little more, less making a value judgment there. Your amount of free time goes down, right? There's more homework, then you'll have less free time. If you had no homework, you could say you had infinite free time, right? And if you have an infinite amount of homework, you will have 0 free time, right? So one goes down. In fact, to properly model that, it's not a negative linear thing. What we need is an actual inverse graph, right? It looks like this. That is 1 over x, right? Oh, there's that rational function making its appearance yet again. That's what we really want to show, because we want to still be within the realm of positive numbers. I'm not talking about, like, you get a negative amount of free time. That doesn't make any sense. No. But on the scale, as I go further and further out this way, I go further and further down this way, right? Slide down instead of increasing. That's the inverse variation, inverse relationship, as opposed to a direct one, right? As one increases, the other increases. This can very generally describe just about anything, and I can't get my arrow to actually line up. That's better. You can describe so many things as a direct or an inverse relationship. But that's only if you isolate just those two things. How does this compare to that? In reality, the amount of free time you have available depends not only on how much homework you were assigned, right? But how much sleep you're getting, okay? How much energy you have for the day, right? What chores you have to do, all these other things that eat into your free time. And of course there's a cap, there's only so many hours in the day total, so there is a limit here. But all of these things factor in and affect how much free time you'll actually have left at the end of the day. So we would call that a joint variation, right? There's multiple independent variables, right? So whereas the direct variation says y is proportional to, that's not a good proportional to, there we go, is proportional to x, and inverse says y is proportional to the inverse of x. The joint variation says that y is proportional to like x and z, multiple things. This little symbol means proportional to. We're not talking about an actual equation just yet. We're just talking about the relationship, okay? It is still a multiplicative or a divisional thing. If x increases, in order to maintain a potential equation, y must increase. In fact, let's go ahead and make this an equation. To make this relationship an actual equation, we're going to add a constant here. K for constant, because Germans, actually. Okay? So we'll just change all of these into equations, and we'll add our constant K. And the constant could be anything, right? In this case, look at the direct variation. you're most familiar with, just a straight line. The k would be your slope, right? Some things, right, might increase dramatically with increases in x. Other things, only very small increases compared to increases in x. And that how much it increases depends on the size of your constant, right? And you could have the similar result here. Our k affects how much change, or how drastic. Okay. And the other thing we can do here, our joint variation is not limited to just multiple direct variations. We could also go 1 over w. And so really we would write that all as one ginormous thing, constant times variable x times the variable z, all divided by the variable w. Okay? In fact, I'm going to steal that as another example here. And let's make it green, because this is what you will be tasked with today. You will be given a real, live physics equation and asked to analyze said equation and tell me what is related to what. Okay? In this case, you would write a sentence that says y is, or varies directly with x. You can say y varies directly with z, and you can say y varies inversely with w, right? All of those relationships are wrapped up and tucked inside this neat little compact package of an equation. This is the beauty of equations, right? They are shortcuts. This is why we have this mathematical notation in the first place. Mathematicians are as lazy as possible. If they can avoid writing full-out sentences, we will. Okay. So yes, there's other ways to write it. You could combine these, right? And you can say y varies directly with x and z. That could be acceptable, right? Why do you have to rewrite half the sentence all over again? Just use the word and, right? Those are both direct variations because they're multiplied by the constant. Okay? Think about comparing to the constant. If I take the constant and I multiply by my variable, it's a direct variation. If it's the constant divided by my variable, well then it's an inverse variation. Okay. Any questions so far? No? Okay, then let's look at the actual questions for today. I have given you an example right there. So here we have this V with a bar over it. We have a triangle S. What the heck is all of this? Oh my gosh. Well, physics equations introduce a lot of the Greek alphabet. Okay, and you're just going to have to get used to that. This is the Greek letter capital delta, and it represents change in. And actually, you might have gotten that one from chemistry already. I'm not sure. It'll show up there, right? And so I think you can probably understand this equation. Most of you already know this, right? The velocity, okay, another type of speed, it's actually speed with a direction, okay, is your change in position over change in time. How far did you go versus amount of time that passed, right? How fast is the car traveling? 55 miles per hour, right? Distance divided by time is your speed. And so what this equation is saying, more specifically, is that this symbol means average velocity varies directly, okay, because this is being multiplied up here, with respect to displacement, change in position, and it varies indirectly, inversely. Maybe I should have said inversely. I bet I will need to go change that in the type up, right? Inversely with respect to elapsed time, right? Because time is being divided here. So you could say change in time. I wanted to treat it as a adjective on time, so I said elapsed time. Okay? So that's what you're going to do. You're going to write these kinds of sentences that relates the quantity on the left with each given quantity on the right side. I have told you what all of the symbols mean. So for number 1, the symbols in order represent net force. So this is Greek letter sigma. Sigma F means net force equals mass times acceleration. We've got momentum equals mass times velocity. Centripetal acceleration, notice the little subscript C there, equals velocity squared divided by the radius. We've got average acceleration equals change in velocity over elapsed time. And force of gravitation equals the universal gravitational constant. I've underlined that for a reason. Big G here is a constant times mass 1 times mass 2 divided by radius squared. And here finally we have period equals 2. I hope you can recognize 2, integer, it's a constant, right? Times pi, also constant, times the square root of length, yeah, and acceleration due to gravity. And it doesn't show up well in the computer version, but all of that is underneath the radical. The L divided by G is within the square root. Okay, so I hope I've given you verbally, you've got it written down what all the symbols mean. Go ahead and the rest of your task for today, and this is your homework, is just to finish this worksheet, is go ahead and turn all of those equations then into sentences like in the example. Please use inverse, not indirect. I messed that one up. In fact, do I have... Oh good, I did share it as the doc. I can go in and edit this. There we go, inversely, fixed. You can go ahead and reload and re-download that with the edit. All right,